In this next segment, we're going to start to look at the weighted average cost of capital equation, and we'll look at each of the inputs to the equation, break them down so you know how to find those inputs, and then we'll create some numbers and we will look at then the outcome of the equation, and we'll talk about how to interpret the outcome of the equation. So I'm going to go ahead and share my screen, and you should see the weighted average cost of capital equation now. So let's start by recognizing that we're starting to deal with time value of money equations. And we're going to look at those heavily in this coming week, and we'll use them heavily throughout the remainder of the course. In a time value of money equation, as you likely know, there's the need to apply a discount rate. And a discount rate might take many different forms. Discount rate might be inflation. It might be an interest rate. It might be a personally chosen rate that's your opportunity cost of capital when you're thinking about what rates you would invest. It might be imposed as a hurdle rate of some kind or a required investor return. But when we're looking at these metrics and we're doing so from the standpoint of the firm, then we need to recognize that the firm's cost of capital, its opportunity cost for the monies that are invested in and through the firm, is the firm's weighted average cost of capital. To be able to calculate this, we first need to understand the value of each of the capital components so we can identify their weights or the percentage of the entirety each of those components represents. And then we need to understand the cost of each, and then we can put together the weighted average cost. So let's look at this. Here I've given you the weighted average cost of capital equation, and the equation is E divided by V. By the way, E stands for common stock, the market value of the firm's common stock. I don't know why it's used commonly as E instead of C necessarily, but when we see E, it means common equity. It doesn't mean all equity, it means common equity. So E divided by V, wherein E plus P, or the market value of the firm's preferred, plus D, or the market value of the firm's long-term debt, those together sum up to V. So V would simply be the value of the firm's capital components. And if we have E divided by V and P divided by V and D divided by V, each of those terms would then represent the percentage of each of those components has of the entirety of the firm's capital components. And together, E plus P plus D equals V. So that means that E divided by V plus P divided by V plus D divided by V should equal 100%. So we're capturing all of the firm's capital components within this. Well, each of these terms then, we're going to interact with a cost or return function of some kind. So we'll interact the firm's common share weighting with the opportunity cost of its common shares, its preferred share weighting with the opportunity cost of its preferred shares, and its debt weighting with the opportunity cost of its debt. And we're going to then multiply that by 1 minus a tax rate. And the tax rate in this case is going to be the tax rate on taxable income. And so this creates an after-tax weighting and cost, which is realistic for us because we know that debt, which the cost of debt effectively is interest, and interest is tax deductible before taxable income for the firm. So here's the equation. We'll come back to this a couple of times as we go through these segments, but I wanted to introduce it to you so you can understand where we're going next. And that is, we're going to start to take a look at the market value of each of the capital components. And we're going to start that with taking a look at the market value of long-term debt. First of all, we need to identify which of the firm's debt components can we realistically find a market value for. And I will tell you immediately that we can find a market value for marketable bonds that the firm has. Well, what are the components of a marketable bond? There's a face value. So an amount that an investor loans to the firm effectively when they buy a bond, when they buy it from the firm, not the open market, but when they buy it from a firm. Typically that's $1,000 in the case of a bond, a marketable bond. There then is an interest rate that is stated at the time that the bond is issued. We call that the coupon rate. There is also then the interest rate in the market today for that type of bond. Maybe this bond for our firm was issued 10 years ago at a 10% rate, but interest rates have changed since. So the current prevailing rate in the market, or the current yield in the market for that type of debt instrument for our subject company, will be considered as the yield to maturity in our equation that we're going to look at in a few minutes. And that's a required element so we can find the market value of the bond. We know that bonds are interest only, or at least 99% plus of bonds are interest only. And so anytime we have an instrument that we know its face value, we know its coupon rate, we know the market rate that would be charged if that instrument was to be acquired in the market today, we know that it's going to mature at a certain point in time, and we know that it makes interest-only payments a certain number of times a year. And in the case of bonds, bonds make interest payments twice a year. There's a very small grouping of bonds that has a different number of periods per year, but it's a very small grouping. So we're going to make the assumption that all of our bonds that we'll deal with in this class will have interest payments twice a year, just as we'll make the assumption that all bonds we'll deal with in the class are interest-only bonds, and we'll assume that they all have a $1,000 per bond face value. Well, with those elements in place, we can find a market value. But not all debt that the firm has, and when I say debt, I'm talking about long-term debt. I'm not talking about current liabilities. Not all debt that the firm has fits that set of criteria. So let's look at each of them for a moment. Bank loans. So for bank loans, we're going to use the book value of a bank loan, the book value that we would find on the balance sheet, as though it is the market value of the bond, or of the bank loan. We know it may not be, but we're going to make that assumption, assuming it's fully amortized. So assuming it doesn't meet the interest-only requirements, etc., of a bond. If it does meet the requirements of a bond, then it's just a different kind of bond, and we can go ahead and calculate a value for it. But most bank loans don't. Most bank loans are interest only. Some bank loans are at adjustable rates. So we're going to use the bank loans book value as though it were the market value. Credit lines. Well, we're also going to use the book value as though it were the market value, but for a different reason. Something that you may realize about credit lines, and a credit line is a flexible amount of credit that a client can take out from a bank of some kind, and kind of like a credit card, you can use it all one day, you pay some of it back, you use more of it, it's in, it's out, and so there's no certainty as to how much the business owes the bank on any given day. The credit line has a maximum amount. The credit line probably has a specific period of time for the contract that is based upon. Typically, that's a 10-year contract. Most credit lines, you must make interest-only payments at the very least, typically each month, not each 6-month period of time, and certainly not each year. But in almost all cases, because of the variability of the amount outstanding, it could be $1 today, it could be $10 million tomorrow, and it goes back to $500,000 the next day, all depending upon the amount of money that the business needs to borrow at any moment in time for its cash needs. We know that the variability of the dollar amount has to be aligned with a variability of rate, because the bank doesn't know for how many days or months or maybe even years how many dollars are going to be outstanding. So in the case of a credit line, credit lines are almost always adjustable rate. Well, in that case, the interest rate that is on the contract and the rate that you would get in the market on any given day for that kind of debt are always the same. And when that's the case, the market value and the book value are also always the same. So it's not just that we'll take book value as though it were market value, but literally book value is market value when it comes to that kind of a credit line. And most credit lines fit the parameters that I just referenced. Next, we'll consider notes receivable. Well, a note receivable is just a long-term account receivable. And yes, it is long-term debt, and it most often has an interest rate associated with it, so we will count it. But we don't necessarily know, and looking at the balance sheet, is this one that's interest only? Is it extending for a year, for 5 years? Sometimes they're flexible, sometimes not. Sometimes they're highly contractual, sometimes not. So we're going to assume that the book value of a note receivable is its market value. And we'll take it as though it's its market value when we do our calculations. So for these first three items, bank loans, credit lines, and notes receivable, we will make the assumption that the book value on the balance sheet for these debt instruments is also the market value. Well, what about mortgages? Well, for a mortgage, we're also going to make the assumption that the book value of a mortgage on a balance sheet is synonymous with its market value. But we'll make that assumption for somewhat different reasons than we did for the first three. Partially because a mortgage has an underlying piece of collateral by definition, that's real estate. And we now know that sometimes when a bank is in a position where the underlying value of the collateral, the real estate, is less than the actual amount of the contractual debt, that all kinds of rules start to be broken. We saw these in 2007, 2008. Companies and banks started calling these loans, started foreclosing on these loans, started requiring different criteria on these loans, such that you couldn't just nice and neatly give them a value. I might have a $500,000 loan against my home, and I might call that a mortgage. Well, I got it when my home was worth $700,000. And so clearly, the book value of that loan was at least its market value. And I would tell you that the book value was its market value at that moment in time. However, let's assume now that the housing market falls apart and that loan of $500,000 is collateralized against a property worth $400,000. Well, we know very well that if the owner of the property goes to sell it, they'll need permission from the bank. The bank is almost certain to give them that permission because the bank already knows that it's sitting on a loan that has bad collateral against it, and they're going to write a bunch of this off. So there are some rules and there's some issues with respect to mortgages that make them just enough different. Not only the collateralization issue, but how they're packaged into portfolios and pools, some of the derivatives that are run from them, some of the guarantees that are associated with them, etc., that make it very challenging to get a market value on any given borrower's mortgage, even if we know the underlying value of the real estate. Those don't always line up nice and neatly. So we will, again, just like we did for bank loans, credit lines, and notes receivable, we'll take mortgages as though the book value of the mortgage or the amount outstanding at any moment in time on the balance sheet is going to be equal to the market value. Well, we already talked about market value of bonds. We have a calculation for that, a nice, neat, clean calculation that we'll actually go through. So when we look at market value of the firm's capital components, the first one we're examining is debt. And the first four elements of long-term debt, we'll consider those, bank loans, credit lines, notes receivable, and mortgages, as though the book values on those are the market values. And we'll then suppose that the market value of a bond, the fifth type of long-term debt, the book value may well be different than the market value. And we identify the market value by using the bond value calculation. So let's look at that again, or let's look at the calculation. This is one of the components to WACC, of course, because the bonds are one of the components to capital debt, and debt is one of the three capital components in the WACC equation. So when we look at the market value of bonds, we're looking at an equation that is equal to C, and C means the coupon payment, not the coupon rate, but the coupon payment, C times 1 minus 1 divided by 1 plus YTM to the power of N, all of that divided by YTM. Now I will tell you that this first part of the equation, so the left-hand part of the equation, is the present value of the interest stream to investors for owning the bond. So this is on a per bond basis. This is the coupon payment per bond. This is the number of periods the bond has between now and the end of its life cycle. This is the YTM, the yield to maturity. And the yield to maturity is nothing but a time-adjusted form of the bond's current yield, or the yield that kind of debt would receive in the market today. So this left-hand side gives us what the income stream that the bond pays an investor gives that to us in a present value form. Plus, then we know the bond is going to pay off at $1,000 when it matures, and we're going to take that 1,000, or F, face value, and divide it by 1 plus the yield to maturity to the power of n. This equation in the whole will give us the market value of bonds. However, unless you understand what each of the variables represents and how to find them, the equation itself isn't all that valuable for you. So let's look at that. So C, which is a coupon payment, is equal to the face value of the bond, $1,000 in our case, times the coupon rate of the bond. So let's assume for a minute that the bond was issued at a 6% coupon rate, which means that it's going to pay 6% interest per year. And if bond is paying interest twice a year and it's doing so on $1,000, then that's going to be broken down into 2 equal interest payments to the holder of the bond of $30 each. So the coupon payment, it comes from the dollar value of the face value times the coupon rate divided by the periods per year. Well, face value, as I've already told you, is $1,000, and we'll always assume that the $1,000 is constant for this. We then have yield to maturity to consider. And yield to maturity is simply a time-adjusted form of current yield. So literally, we take the current yield, or the current market yield for the bond, and divide it by the periods per year. So the number of interest payments it makes is periods per year. So this will universally, for our purposes, this will be true, or be 2. Again, this is the current market yield. This is the rate that this corporate client would pay if they were trying to borrow this type of money in the market today, not the coupon rate. That was an amount identified by contract or debenture when the bond was transacted with the company. But now time has passed, rates have changed, and so we have this difference between the coupon rate and the current yield, or yield to maturity. And by the way, it's the friction between those two values, those two numbers, those two rates, that sets up the change in market value for a bond. When interest rates go up after a bond is issued, the value of the bond goes down. When interest rates go down after a bond is issued, the value of the bond goes up. In fact, we can say that about virtually all debt instruments. When the debt instrument would warrant a different interest rate today than it did at the point of issuance, then its value in the market would have changed if we can reasonably measure its value. And if rates go up after issuance, the value goes down. If rates go down after issuance, or if rates go down after issuance, the value goes up. Well, let's give an example of this. So I'm using this example, and you'll find this within the Mira-Dravana case. Let me bring that up for us for a moment. And I'm looking right now at the numbers that we see represented right here in the Mira-Dravana spreadsheet. So this is where I'm getting this data from, and you're going to find that this is going to give us the market value per bond for Mira-Dravana. Mira-Dravana took out these bonds with a 14% coupon rate, high rate, did so with the bonds, for bonds of the type of which today, if Mira-Dravana borrowed that money, they'd be borrowing it at 6%. So we know rates go down, values go up. So we're going to make an assumption that when we calculate this value, that what started out as $1,000 face value would likely have a market value of much greater than $1,000 today. We're assuming that it's paying interest twice a year. We're assuming that this 30-year bond, and not all bonds are 30 years. Some are 10, some are 5, some are 15, 20, 30. But in this case, we know this is a 30-year bond. It was issued in 2004. Well, if it's issued in 2004, and here we are in 2019, there's 15 years in between those two periods of time. So we know that the N is going to be 30, or 15 times 2. And here we have the face value of 1,000. So let's walk through and see how this comes together. So again, our face value of 1,000, periods per year of 2, the coupon rate of 14% or 0.14, and this is the contractual interest rate, and that's going to conspire then to give us a coupon payment that is going to be equal to not $140, but $70. So 14% times a $1,000 face value divided by 2. We've got a 6%. We're going to then put all this together. So our C is 70. Our yield to maturity, which remember is the current yield divided by the periods per year, so 0.06, not 6%, not 14%, but 0.06 divided by 2 gives us a yield to maturity, or YTM value, of 0.03. Now we know that that's synonymous with 3%, but you have to use it algebraically at 0.03. And then our number of years to maturity is 15, and we have 2 periods per year, and so we're going to have N be 30. As we then plug this into the equation, we see here 70 is C times 1 minus 1 divided by 1 plus YTM, or 0.03, to the power of 30, or the number of periods between now and the time the bond will mature. And all of this divided by 0.03. We see then that the second part of the equation, we have F at 1,000, and this is divided by 1.03 to the 30th power. And then together, those will equal $1,784.02, which, not coincidentally, is the per bond value that we identify for Mira Drovana. Now, it's important for us to consider what else might be relevant here. We have 30,500 bonds. Well, how do we know that? Because we know that there's 30.5 times 1 million, so 30.5 times 1 million, or $30,500,000 issued, loaned to the company when the bonds were issued. And we can now take that $30,500,000, we can divide it by $1,000 per bond, and we now know that we end up with 30,500 bonds. If we multiply that by 1,784.02, that's going to then return a total market value of the bonds of $54,412,538.45 for the bond value. Let's walk through briefly how we did this, and I'm going to bring up the HP calculator to do this. So as we go through some of the different numeric examples over the coming weeks, I will often bring up the calculator so you can see how I got them. You can do this by hand, you can do this by calculator function, or you can do this by calculator just using it to do our multiplication, addition, etc., find our exponents. So a couple of things that might be helpful for you is to understand first how we deal with exponents and how we store numbers in this calculator. So when we deal with exponents, there's a couple of different ways of doing this. I tend to use the y to the x function that's here in red. Y to the x, you see it on the lower side of this particular key that I've got my arrow at in red, which means that to operate that function, we then need to use the red secondary key. So I know that I've got 1.03 or 1.03, and then I want to find the value of that to the 30th power. Well, I do that by having put in the number. I'm then going to say red, so I operate or I activate that red secondary. Y to the x, so it now knows that I'm looking for an exponent of 30. So I type in 30 and then equals. And it tells me that that's 2.43. So this 1.03 to the 30th power is equal to 2.43. Now the reality is it's equal to much more than that. I want to look at this, let's say I extend this out to the 4th decimal place. Your calculators come such that they are probably set up to show you 2 decimal places automatically. I always use the calculator extended to the 4th decimal place, so that if I'm calculating a percentage and I then times whatever that number is that I want to see as a percentage, I'm going to take that number, multiply it by 100, and if I do that, I still have 2 decimal places of fidelity left when I see the percentage. I'll show you an example of that in a few minutes. Let me show you first how to change this from 2 decimal places to 4. And we're going to say red display 4. And when I do that, again, the secondary red key, display, which you'll notice is the bottom row of keys, second row from the right-hand side, it says DISP. So red display 4 changed it from 2 decimals of fidelity to 4. I could say red display 9 if I wanted to, but I'm not going to do that. So red display 4. So if I want to find an exponent, I will put a number up on the screen. I'll type something in. I will then I'll then hit the red secondary key, and then I'll use the red y to the x. I'll then input the exponent, so 30, 15, 12, whatever it happens to be, or in the case of a root, I'll put it in as a decimal equivalent. If it's a squared root, then that is equal to 0.5. A cubed root is 0.333. A quad root is 0.25, etc. And then I'll hit the equal sign. In this case, it gave me 2.4273. I don't want to keep writing that number down, and I don't want to keep having to try to remember that number, nor do I want to lose some of the numeric fidelity. Remember, when I showed this as red display 9, it told me that the number wasn't what we just saw it as. It's a much different number because we have a lot of fidelity or additional numeric information out here to the right that we lose when we have it truncated to the second or the fourth decimal place. I'm going to put this back, red display 4. And I want to store that number in memory. Well, when I store a number in memory, it will store not just the item you see on the screen, it will store the entirety of that value with all of its decimal equivalent. So to do that, I'm going to use the memory keys. And think of these keys as drawers in a dresser. And I have drawer 0, drawer 1, 2, 3, all the way through drawer 9. And I can put one item in each drawer at a time. And the way that I do that is I have something on the screen that I want to memorize. I want to store it. And I will hit the red secondary key, activate the STO function, which is in this fourth row of numbers or of keys down, second from the left, so STO function. And then I'll tell it which drawer I want to put this in. So I'm going to put this number 2.4273 into drawer number 1. So now if I clear this, and clicking the clear one time simply clears the register, and I then put up some other numbers, I finish those, and if I want to bring back that number I had, I'll simply go ahead and say recall, RCL. Notice I'm not having to pick up a secondary key because recall is in white. So RCL 1. And the number with all of its numeric fidelity, regardless of what's showing on the screen, the number has been brought back to me. Well, I'm gonna motivate this equation again. That's what we're working on. And to do that, I've chosen the most complex number first. So now I'll start the equation. I'll hit clear, and I'll say 1 divided by recall 1 is equal to. So I now know the value of this fraction, 1 divided by 1.03 to the 30th power. And it happens to be 0.4120. I want to take that now as a negative value. See this little key right here above the blue key? It's got a plus minus on it. That's a toggle switch. And if I have a positive number on the screen, I click on that, it turns it negative. Or I have a negative number on the screen and click on the plus minus, it turns it positive. Well, I'm going to go ahead and convert this 0.412 to negative 0.412, to which I am now going to add 1. So I took that number plus 1, so it's a negative plus a positive. And I now know that the value in the bracket here is 0.5880. I'm now going to go ahead and divide this by 0.03. And I now know that this super fraction here is 19.6004. I'm going to multiply that then by 70. And I now know that the value of this left-hand term is $1,372.0309. I'm going to store that number. Well, how do I do it? I've got a number on the screen. I'm going to click on the red, storage, and I'm going to put it, in this case, in bin number or drawer number 7. Okay, so now I'm going to go ahead and calculate what we've got going on the left-hand side. So 1,000 divided by, now remember, I already have the 1.03 to the 30th in my memory. So I'm going to divide it by, I'll say recall 1 equals, and I now know that this right-hand side of the calculation here is equal to 411.9868. And I will then store that, red storage 8. And with it still on the screen, I will then say that I want to take this number plus, I'm going to recall the original number for this side of the equation, equals $1,784 and 0.0177, that rounds to 0.02, so it's the same number I calculated over here. Well, I know already that I have 30,500 bonds. I identified that by taking the book value of the bonds times the scale, which in this case was $1 million, and divided that by the face value of the bonds. So I have 30,500 bonds. I now know the dollar amount per bond, multiply it by the 30,500, and it tells me I have $54,412,538.45 worth of bonds. I want to bring this back now so that I can fit it into the other kinds of numbers that I'm using from my financial statements. And remember that those numbers were all in the scale of 1 million. So I have to take this actual dollar value and divide it by 1 million. So I now know that the market value of my bonds when looking at a $1 million scale is 54.413. Well, in this case, I also have some mortgages on the balance sheet. Let's look at the balance sheet again real quick. You'll notice that I have a mortgage, and we're going to take the mortgage's market value and book value as the same dollar amount, and I have some bonds. So to find the market value of the company's debt, I will take the book value of the mortgage, and remember that this is already in the scale of 1 million, plus the market value of the bonds, which I've converted back to a scale of 1 million, and it tells me that I got 58.733 in the market value of the firm's debt. So one of my 3 capital components I've now calculated. Well, the other 2 are going to be simpler for us. The other 2 are going to be the market value of the common equity and the market value of the company's preferred stock. So let's go back to our financial statements, and you'll identify here that I've actually already given these numbers to you. Well, you helped calculate them, of course, but you saw them earlier. We have 55.7 shares outstanding. We have that at a price of 4.125 per share, and the number of shares outstanding times the price per share equals the market value per share for our common equity. So 229.763. For our preferred equity, we have 4.3 shares outstanding, and again, this is 4.3 million shares, just like this was 55.7 million shares, but 4.3 million shares times $2.5 per share, and that's going to then yield a market value of 10.75 or 10.75 million, which then, if I take the market value of the common equity plus the market value of the preferred plus the market value of the debt, I end up with a market value of all the firm's capital components of $299.245.